Hello students, this is part 2 of my tutorial to help you understand how to write chemical formula of ionic compounds. In this part, I'll be explaining how to write chemical formula of ionic compounds which have transition metal atoms and how to write chemical formula of ionic compounds which have polyatomic ions. So let's first see how to write chemical formula of compounds which have transition metal atoms. So where are transition metal atoms in the periodic table? Do keep in mind that this is a simplified version of the periodic table. In this version of the periodic table, we see that there is a block of elements which are sandwiched between group 2 and 3 and which have not been assigned a specific group number. These are the transition metals. Now, transition metals are quite distinct from the usual metals that you come across in group 1 and group 2 of the periodic table. Their chemistry is quite complex, and one of the things that makes their chemistry complex is the fact that they show variable valencies. For example, iron is known to show a valency of 2 in some compounds and a valency of 3 in other compounds. That's because, unlike usual metals, they can lose electrons from two electronic shells. The reason as to why transition metals can do this while others can't goes beyond the scope of the syllabus. But if you do intend to take chemistry in IBDP, you will definitely understand as to why transition metals can lose electrons from two energy levels. Now, if transition metals can show variable valency, how do we write the chemical formula of a compound which has one of these atoms? So the convention is that the specific valency of transition metal to be used is shown as a Roman numeral within a parenthesis. For example, in this particular case, nickel 2 chloride, we see that nickel is a transition metal. So we write its symbol, which is Ni, and this Roman numeral 2 is actually its valency, which is shown in this particular compound. So this value will be specified in the question. The other element that's present here is chlorine, which is present in the form of chloride. So we know that chlorine is in group 7 of the periodic table, and we know that if an element is present in group 7 of the periodic table, then its valency is going to be 8 minus 7, which is 1. So we write the symbol of chlorine, which is Cl, and we write the valency, which is 1, and then we cross multiply these two, just as before. So the valency, when cross multiplied, results in the chemical formula NiCl2. To remember that this 2 is a subscript. Let's take another example. Let's take the case of iron 2 sulfide. So this is where iron is placed in the periodic table. In case you are wondering as to why the symbol of iron doesn't actually resemble its modern name, that's because it's derived from its Latin name, which is ferrum. Anyways, coming back to our problem. So The symbol of iron is Fe, and the valency that is being shown in this particular compound by iron is 2 as shown by the number in the parenthesis. The other element which is present is sulfur, which is present in the form of sulfide. So sulfur is again present in group 6 of the periodic table, and we know from our prior knowledge that for an element that is present in group 6 of the periodic table, the valency is going to be 2. So we write the symbol S and the valency 2. And we also know that in the context of ionic compounds, the formula is the simplest whole number ratio. So that means these two kind of cancel out each other and we multiply these ones. So the chemical formula is FeS. Let's take another example. Let's take the case of chromium 3 oxide. I would like you to pause this video and try to do this question yourself before continuing. Alright, so we see that chromium is a transition metal again, and its symbol is Cr. And as is shown in the name, the valency that is being shown by chromium is 3. So we write 3 here. And the other element that's present is oxygen, which is again placed in group 6 of the periodic table. So its symbol is O and its valency is 2, and we cross multiply these two and the chemical formula is Cr2O3. I hope that's clear. Let's take another example. Let's take manganese 4 oxide. So manganese is placed right here. It is also a transition metals and its symbol is Mn. The valency that is being shown in this specific compound is 4. So we write the 4 here. And the other element that's present is oxygen, which is present right here. And just like in the previous question, its valency is 2. Now a word of caution. Before we go ahead, we again need to verify if that cross multiplication is going to lead to a simple whole number ratio. If we go ahead with these values and cross multiply, we get the formula Mn2O4. But this doesn't align with the convention that the chemical formula of an ionic compound has to be the simplest whole number ratio between the ions. So this is incorrect. So what do we do then? We divide both of them by 2. So the simplest whole number ratio is not actually 4:2 but 2:1. So we cross multiply the 1 and the 2 to get the answer MnO2. So the correct chemical formula of manganese 4 oxide is MnO2. Now let's make a note of some transition metals which are known to show very common specific valencies. So the most common valency that copper shows in its compounds is 2, zinc is also 2 and silver is 1. In fact, if unless specified, use these values as the valencies of these elements. The reason why I am sharing this is that because these valencies are so common for these metals, sometimes in the context of these metals, the valency is not shown in the parenthesis. So let's see this using an example. For example, if I have to write down the chemical formula of silver bromide. Now silver is placed right here. It is a transition metal. But to our surprise, we don't see any Roman numeral in parenthesis in this specific compound. That's because the valency that is most commonly shown by silver in its compounds is 1, as explained in the previous slide. So we write the symbol of silver, which is Ag, and we write its valency, which is 1. So this is something that you must commit to your memory. The other element that is being present in this compound is bromine in the form of bromide. The formula or the symbol of bromine is Br, and because it's placed in group 7, its valency is going to be 8 minus 7, which is 1. So both of them are 1, which means the formula of silver bromide is going to be AgBr. I hope this is clear to everybody. Now let's discuss the case for writing chemical formula of compounds which have polyatomic ions. So let's see what these polyatomic ions are. Now, usual ions such as O2 negative are just made of a single element. As you can see in this case, it is just oxygen. But there are ions which are made up of two or more atoms of different elements. Such ions are called polyatomic ions. For example, the case of sulfate. We see here that sulfate is clearly an ion because it has a charge of 2 minus. But at the same time, this 2 minus is not just carried by oxygen. It's not just carried by sulfur. It's carried by both of them collectively. So a single sulfate ion is essentially one sulfur combined with four oxygens, and this entity carrying a charge of 2 minus. That is how you should understand polyatomic ions. Similarly, you have nitrate, another very common polyatomic ion. We see that nitrate has one nitrogen and three oxygen, and the total charge is negative, which we know is minus 1. So how we should understand this to be is that this is essentially one nitrogen combined with three oxygen having a resultant charge of 1 minus. I hope you can make similar correlations with the other polyatomic ions. Now, one polyatomic ion that stands apart from the others is ammonium. And the reason is that while other polyatomic ions have a negative charge, ammonium has a positive charge. Now let me make one thing very clear. You do not have to commit the formula of these polyatomic ions to your memory. These will be provided in the examination, either in the question itself or in the resource booklet. So the next question is how to assign formula to a compound which has one of these. Let's explore that using some examples. So let's say I have to write the chemical formula of sodium sulfate. So if you refer to the periodic table, sodium has the symbol Na and it belongs to group 1 of the periodic table, which means its valency is 1. Now we look for sulfate in our table. We see that this is sulfate. So we write SO4, and just as we discussed for ions, essentially the number that is present in the charge, the number that is present in this charge, the magnitude of the charge is the valency. So the valency of sulfate is 2. So we write that 2 and then we cross multiply. Obviously, if we multiply anything with 1, it's going to remain the same. So the formula of sodium sulfate is Na2SO4. Before going to the other examples, I would again like to emphasize that the valency of the polyatomic ions is basically the magnitude of the charge or the number that's associated with the charge. For example, the valency of sulfate is 2. The valency of nitrate is 1. The valency of phosphate is 3. The valency of hydroxide is 1. The valency of carbonate is 2, and that of ammonium is again 1. Let's use these in other examples. Let's take the case of calcium nitrate. Now, if you refer to the periodic table, you will see that calcium has the symbol Ca and it is in group 2 of the periodic table, which means its valency is 2. Now, the other entity that's present in this compound is nitrate. So nitrate is NO3, and just as we discussed before, the magnitude or the number associated with the charge that's in the superscript, that's the valency. So the valency of nitrate is 1. Now, if we were to multiply this mathematically, what some students might do is multiply the two separately with nitrogen and separately with the 3 oxygen, and so the O formula might look like this. And mathematically this is not wrong, but again we have to follow the conventions. And as per convention, this kind of representation is wrong. In the context of polyatomic ions, if we multiply a polyatomic ion by a factor which is greater than 1, then we have to put the entire polyatomic ion, so in this case NO3, within a parenthesis and then put the 2, which in this case was to be cross multiplied, as the subscript. Again, I like to repeat, if a polyatomic ion is multiplied by a factor greater than 1, then instead of multiplying the factor with all the atoms separately, what we need to do is we need to put the polyatomic ion within a parenthesis and then put the factor that we are multiplying as a subscript. So the formula of calcium nitrate is CaNO3 whole twice. That's the way it's read out. Now let's write the chemical formula of ammonium chloride. So if we see ammonium can be represented by NH4, and just as we discussed before, its valency is 1 because the magnitude of charge is 1. Why are we writing before? That's because it has a positive charge. By convention, ions with positive charge are written first and ions with negative charge are written later, just as we write in the name of the compound. Now, chloride is of course derived from chlorine, which has the symbol Cl, and if you refer to the periodic table, it's placed in group 7 of the periodic table, so its valency is going to be 1. So now it's 1 on either side, so we can simply write NH4Cl. Now, some of you might think as to why did I not write it like putting a parenthesis and this. That's because we are multiplying with a factor 1. As I said before, the convention is that first of all 1 is never written as a subscript when writing chemical formulas, because it is understood that if you don't write a subscript, that is 1, and since we are not doing it, you do not need to put a parenthesis. Alright, so a parenthesis needs to be put when you are putting a subscript next to a polyatomic ion. Since 1 is never placed as a subscript, you don't need to put a parenthesis in, and in fact if you do, that's considered wrong as per conventions. So the formula of ammonium chloride is NH4Cl. Let's take one more example. Let's take the case of ammonium carbonate. I would like you to pause the video and try this yourself before I reveal the answer. Alright, so I think you may have tried this yourself. Let's try to write the formula of ammonium carbonate. So ammonium is NH4 and its valency is 1. Carbonate is represented by CO3. I think I should need to write this again. So CO3, and the valency is again the number associated, which is 2. Now the interesting thing in this compound is that both the positive ion and the negative ion are polyatomic ions, right? So again you cross multiply. Now when you cross multiply, again you don't need to put a parenthesis around CO3. That's because it's multiplied with 1. But with ammonium, you do need to put the parenthesis. So the formula of the compound is going to be NH4 whole twice CO3. So I hope these examples and tutorial was helpful, and now you should be able to write the formula of most ionic compounds. Thank you for watching.